So we talked about um, different ways of categorizing epilepsy, primarily into um, generalized or partial, meaning they take up both hemispheres or one hemisphere or less, but also simple and complex, which is whether you lose consciousness or not, or vice versa. And simple you don't lose consciousness, and complex you do. And then there are a variety of ways to categorize epilepsy due to the motor output that could be generated. And then finally, we talked about just a handful of the long list of epilepsies that are would have been in the pie graph I showed much earlier, called the genetic epilepsies. These ones that are associated with a single gene that is usually a recessive gene, and if you get two copies of it, you get the syndrome, right? And so we've known for a long time that there are these kind of epilepsies, um, and but we also knew that most people, nearly everybody who has epilepsy, does not have one of these. So while they were very interesting in the sense that they gave us some insight into what was causing epilepsy, they were also frustrating because it left us very unsure, and so a lot of people spend a lot of time trying to understand why are people having epilepsy if this genetic thing is only, a percent or so of the causes. What causes regular people to have epilepsy? And of course, you can say, well, they had epilepsy after they had a head trauma, so the head trauma caused it. But that's not a very satisfying, sort of explanation, because lots of people get head trauma and don't have epilepsy. Lots of people have stroke and don't develop epilepsy. So, lots of people have brain tumors and those brain tumors removed and don't have epilepsy. So what is the real cause on a cellular level, on a molecular level? What's happening? So this figure here was what I was taught when I was an undergraduate on the right, right? So this is saying in a generalized seizure where we know that both hemispheres, by definition, right, a both hemispheres are involved, there must be some central focus, right? This idea of a focus has been critical to the theories about epilepsy. The idea that there's some little bit of the brain that's gone wrong, that's doing something bad, and it's able to make the rest of the brain have the seizure, right? And this idea of the focus is supported because you can find a focus in some seizures, remove that focus, surgically cut it out, and the person does not have epilepsy anymore. So that in a way, this says this idea is true, okay, that there's some little bit of the brain that goes wrong. On the other hand, you you can't surgically remove. It's only a small collection of epilepsies that we can do this to. Okay, so what this has led to is this idea that we see here, right? So we know that there's generalized seizures, the whole brain is involved. There's some central focus that communicates to the whole brain. Now, we can't remove it because we can't find it, or it's in some super important area, and so we couldn't remove it even if we could find it. And people have sort of waved their hands and say, look, this kind of makes sense, and it kind of does make sense, right? So this was this idea that in a generalized seizure, there was a focus in some deep part of the brain that spoke to everywhere, while in a partial seizure, there was some small cortical focus that you could remove. Um, Now, not to get into the weeds, but people should have realized there was a problem with this sort of idea relatively early on, because one of the most common epilepsies that you can remove a cortical focus from is called medial temporal lobe epilepsy, and it is generalized. It's generalized. It's nearly always generalized, and there is a focus on both hemispheres, right? So you need to do surgery on both hemispheres. So what is the chance, if epilepsy is caused by some little bit of the brain going wrong, just sort of due to you fell on your head when you were 4 years old? What's the chances of it happening in the same place on both sides? Still, this idea is common. If you talk to a lot of people, they will still cling to this idea. But we're starting to realize that this maybe not untrue, but certainly not a helpful or very explanatory idea. And the idea, the thing that really showed that we have some fundamental misunderstanding of epilepsy is this paper here. Okay, so here's this pie chart from before. It says that 2 out of 500, 0.4% of epilepsies are genetic, right? And basically all of the rest is non-genetic. So if 2% of Australians have epilepsy, what is the concordance rate of epilepsy between twins? Okay, so if I'm a twin and I have epilepsy, what's the chance that my other twin has epilepsy? Right, so if this is true, we can do the maths pretty simple, right? So for 96% of the patients, i.e. the rest, the non-genetic, the concordance should be 2%, right? Because it's not really related to anything to do with genes. So, maybe we could say because they grew up in the same environment, it should be a little bit more than 2%. But for 0.4% of the patients who have this genetic case, it should either be 100% for identical twins, monozygotic twins, or 50% for dizygotic twins. And we can sum those up and we basically get that it should be about just roughly 3%. Right. And you could say, oh, well, it probably should be the concordance should be slightly higher than 2% for twins because, they grew up in the same environment. And if it was some chemical or some diet, it should be higher. You can bump that number up a lot. Let's say it's 5%. Let's say it's 10%, right? The numbers that you get are still pretty low. But when you measure it, the concordance rate for generalized epilepsy between monozygotic twins is 80%. Okay, so it's so far away from what is predicted by the theory that you can say, look, even if we've got some of these numbers a little out, there's no explanation for this, right? That if 80%, this is what you see down here, of if generalized epilepsy is 80% concordant in monozygotic twins, there must be a massive genetic component. Even if you just see it all seizures, right? So in monozygotic twins, there's a concordance of 64%, and dizygotic, it's 20%. So it's so far above what you predict. The only one that is sort of interesting and close is the concordance for focal epilepsies in dizygotic twins, which hits basically where you would predict. But still, you go back to monozygotic twins and you've got 40% concordance. So there is a massive genetic component here. Indeed, this leads to a new idea that basically generalized epilepsies are a genetic disease. And in fact, you can even see this in a lot of focal epilepsy. So this is just post-stroke epilepsy. So after your stroke, do you develop epilepsy? And you can see that 10 years after a stroke, you're up to 10%, nearly 20% likelihood. But that there's a significant difference in that development depending on whether or not anybody in your family has ever had epilepsy. Now, one thing we need to be the 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 interpretation of genetic data is something that bamboozles a lot of scientists, and I'm not going to pretend to be an expert in it, right? Firstly, the first thing you need to sort of grasp is just because you say a disease is genetic doesn't mean it's Mendelian, doesn't mean it's caused by one gene. Okay, it could be caused by hundreds of genes. All right, and this idea is still something that a lot of scientists struggle to sort of conceptualize. The other thing is just because it's genetic doesn't mean it was given to you by your parents. So there's estimates that are maybe 10% of focal epilepsies were caused by a de novo mutation, so a mutation in the germline. And what are these mutations? Well, unsurprisingly, probably, at least to me, huge numbers of them are in ion channels. Voltage gated ion channels we see here, and the ion channels at the synapse we see there. We see mutations in the in some of the proteins involved in the release of vesicles, the reuptake of vesicles, SNAP25, and vesicular release. This mTOR pathway that's beyond me, right? But is an incredibly important cellular pathway, and we even see a few in epigenetic chromatin remodeling proteins. Okay, so but again, it's we need to get away from this idea that this epilepsy was caused by a mutation in the GABA A alpha 1 subunit. It's more about an accumulation of mutations, or I shouldn't even call them mutations, accumulation in alleles that increase your risk of developing epilepsy. And as you get more and more and more of them, your risk increases and increases.